Well, I wanted to replicate with this script a table that I asked you to uh, analyze while reading this paragraph 8.4, because this paragraph is very important to finalize our course. We've been doing a lot of steps towards this, and this is the logical finish of our path, and this is very nice that we managed to um, do this on time, because the next part of this book, if you follow if you continue doing this, the next part of this book concentrates on more advanced methods in econometrics, and my plan is to do all the other things with you in the second part of econometrics course. Therefore, this is very important to understand the essence of our steps, the essence of our what we've been doing uh, during the during this course. You see that from chapter 9 there is some uh, questions about assessment studies based on multiple regression, more, let's say, logical and theoretical questions. How would you assess these studies? And then it continues with the advanced methods of econometrics, like working with the binary data, or there is a binary dependent variable and something and something. And I really hope that we will do these things together in the next year. So, yeah, so as I said, I try to reproduce or replicate this table partially, not the full similarity, but at least to get these estimation results for different models. So let me comment briefly on this part. So this is the usual part. We are just loading libraries. This is the usual part. We are just loading the table. So nothing is new here. Now, what is going on here? As I said, when you want to create nonlinear regression models, you must produce new variables. And here I define all these variables that are needed for the nonlinear models. So let's observe what kind of regressors do we use here and what kind of regressors do we need to create. So first of all, here they use the logarithm of district income as a control variable, not a district income itself, but a logarithm. And this is a logical extension of what we've been discussing yesterday, because the logarithm, because we observed that income and test score are related non-linearly. And there are two possible ways how we can control for this linearity, either polynomial or logarithm. So authors decided to choose logarithm, and this seems logical because logarithm of income has some economic sense. It's a percentage change in income that leads to change in test scores. So we need to create this log income variable. This is the first line. I guess this is understandable. So you understand what's going on here. I define a new variable which is called log income, and this new variable equals to numpy log of this variable average income from the initial data frame. So the next part, this must be also familiar to you from the home assignment number 3 and also from our previous classes when we define the binary variable. So this binary variable high EL equals to 1 if the percentage of English learners is greater or equal to 10%. So percentage of English learners is given here in percent already. So if it's 12, it's 12%. If it's 68, it's 68%. So therefore, we define it in the following way. There are different ways how you can define binary variable, but I guess this is the most natural, and from the code itself you can understand what's going on. So you take the variable ELPCT, right? So the variable which represents the percentage of English learners. You write this logical condition that this is greater or equal to 10. So let me show you what happens if you ran this part separately. If you ran this part separately, it will produce you logicals. It will produce you true or false. And now if you want to convert these logicals into numbers, 1 or 0, you simply take this in parentheses and multiply this by 1. And instead of true, you will get 1, because true multiplied by 1 is 1, and false multiplied by 1 is 0. So here we are. So here we have this column of ones and zeros. And we define this variable as high L. This is the second step. The third step is to create these second and third powers of STR. So we are trying to model nonlinearity in student to teacher in the class size, nonlinearity in the effect of a class size on a test score. And in order to do this, we create these two variables, and they are created simply. So don't forget, please, that in Python, instead of this sign of hat, while raising to power, we are using two multiple signs to raise to the power. So this means that data str, so variable str, must be raised to the second power, and this must be raised to the third power. So we create new variables for these regressions. So we run this part and then go to the next part. So here I created in the, let's say, nested way the results of 7 regressions. Look, this doesn't differ from what we had before. Let me just show you that I'm doing exactly the same things as before. Just one difference. I'm doing all these things in one line. Look what we did. First step, we defined formula. Then we took this formula and plugged inside the function OLS. Now I did it exactly here. So inside the function OLS, I provided formula instead of creating a separate object of formula, which is totally fine. The next step was to take this model 1 and apply this method fit in order to create the regression results. I'm doing this in one step instead of creating a separate object model. So this is my object model. So this thing, the whole thing is my object model, and I apply this method fit right away here. And therefore, I'm able to create all these things in one step. It looks a bit cumbersome, like difficult to comprehend. Of course, this is easier, and usually it is preferred to do the most simple steps one by one, in order if somebody takes your code and tries to understand what's going on in your code. So this code, of course, is much understandable than this one. But in this case, we are not going to kind of make it nice. I just wanted to produce this in the least possible number of steps. And look what happens here. So the most important part is how would you define the function here, the formula, sorry, here. So this is, so let's see, let's have a look on the first column. So here we regress test scores on STR, on English learners percent, and also on this meal percent of eligible for subsidized lunch. We have Y, which is for yes. So we included this as a regressor. So here we have the model, multiple regression model, with one regressor STR, second regressor ELPCT, and this third regressor MILPCT. Okay, so this is familiar to us. Now, in the second column, we include also the logarithm of average income. So we created this variable earlier. This is the log income. We include this log income into our model, and everything, as I said, will be implemented as before. Nothing new here. So we can compare the first column, the second column with the table from the book, and you see that the numbers are exactly the same. -1 for STR and -0.73 for STR when we control for the district income. And basically, what does this mean? This change in this coefficient. It means that log income, or like not log income, but income, the income in the district, indeed was omitted variable. Because when we decided not to control for this variable, the effect was stronger. We included this variable and the effect went down. And this is the signal that regression in the column 1 has an omitted variable bias. And this omitted variable was these economic characteristics of students captured by income. Is these two steps clear? Results 1, results 2, and the creation of variables. Any questions?
A big question for a big favor. Can you please again describe from the beginning to the end, but I mean in a more general way? I think I didn't catch something.
From the very beginning of this class, you mean?
No, like from the beginning where you added the new parts, like
here.
Yes, from here.
So I did them in advance in order to replicate all these tables and all these regressions. And you see that, for example, in the column number 3, so probably now you will understand. In the column number 3, I want to estimate a regression model when test score is dependent variable. So the test score is dependent variable everywhere, basically. So no need to keep saying this. And included regressors are STR, student to teacher ratio. And now, instead of percentage of English learners as continuous variable, we include this binary variable, which is 1 for districts where percentage of English learners exceeds 10%, and 0 otherwise. So we can change the way how we control for this percentage, either here or here. And now if I want to include this variable into my regression, I need to create this variable first. So that's why I created, so here I created log income, and here I create the this binary variable high L, which is I'm going to include in my regression number 3.
Is that how we were supposed to do in the last home assignment?
Yes,
because
exactly.
I didn't get how to do it. Yes.
And let me demonstrate that you must have been able to do this, because in the as I replied to you in the exercise session number 2, we had already this. We created here. We created these binary variables, large classes, small classes, and we've been doing this somewhere.
You see, it we create we don't include it into the data frame, into the table, like it is in your code now. Previously, So we made just the
Yeah, we divided
array.
them into two parts. I agree with you.
And that's why I didn't know how to do it in the last home assignment, and that's why I asked if the
So it's doing something. So probably in statistics, I definitely did it. Let me see. Maybe in statistics, some of the exercise sessions. Like I clearly remember that it was discussed somewhere. Okay, so it doesn't matter, but I will find it. So otherwise, well, okay, there is not that much points for this binary variable. Don't worry about this. So now we see how you were supposed to do.
yes, it
Or
looks
at least I
nice.
see from your codes that you have a lot of interesting things that we haven't discussed during the classes. So it says me that you are able to find some answers to your questions from the internet. So this is another story. So if you have some,
In my codes,
yeah.
oh, it's strange.
So you suspect that
I usually
someone else was doing this for you.
no, I usually don't use internet for coding purposes. Rarely, I'd say.
I don't know. Okay, but still, I see some nice things in your code, which for me, which means that you are developing your skills somehow. Maybe not from the internet, maybe from some books. I don't know what was the source, but I see that it appears something that we haven't discussed here. Which for me, is nice. I don't mind. Okay, well, and also one thing here, we include this interaction term. So interaction term is another way how we can model nonlinearity. While every time when we include a binary variable, we also want to include an interaction term between this binary variable and regressor of interest, the variable of interest str. And look, please, how we are supposed to do this here. When we write a code, interaction term is given with this colon sign. So you write one variable, then colon, and then the other variable. And this is an interaction term. This is how you include this one regressor multiplied by the other regressor. So never put multiplication sign. It would not work. You need to put this colon sign here. Or you also can create a separate variable in your data frame instead of doing this. But I decided to demonstrate you how you can do this in a more, let's say, elegant fashion.
Does the order matter?
No, it doesn't. No. So let me put the comment here. So the interaction term is given in the formula as this. So we will come back to the interpretation of this regression. Now I'm just describing you what we are doing technically and how we include these things. So basically, I'm keep doing this again and again for all the columns. Here you can see the most important part is how would you include in the formula interaction term, and how would you include in the formula this squared or cubic term. And I created them, and now in column number 5, when we include the polynomial of order 3 for student-teacher ratio, here I use it in the following way. So it's str, str2, str3, because I created before this variable str2 and this variable str3. I am able to include them here. And I keep doing this for 7 specifications. And then using the nice method that we have discussed during the previous exercise session, I created this table put these regressors in the same order. As I said, my goal was not to replicate completely the same view of this table, but rather to show the same results for the regressions. And one additional thing I want to draw your attention here, if you want to round your results, we haven't discussed this last time. So our nice table here contained 4 decimals after the comma. If you want to make it shorter or longer, you can also include this attribute here, float format. And here it's going to be %.2f, where 2 exactly shows how many decimals must be there. So assume that we change 2 to 3, we rerun this, and you see that now table looks like this. So it has 3 decimals instead of 2 decimals. I can change it to 2 and it looks nicer. Because if there are too many decimals, the attention somehow is not working good enough. So by the way, we can observe also the regression diagnostics R squared, and R squared for all the models is quite large. It's around 80%, which means that this model now feeds the data the best we can do. Probably we can do even better, but at least this is very, very nice feed. Remember that we started with R squared about 5%. When we started with the single regressor, it was 5%, and now we improved a fit of our model up to 80%. This is one way.
Include stars.
Yes. Wait. Yes. So this is one way to create these tables, and I created this table without stars. Yes. There is another cell here, and let me comment on this and how this changes. So this one has stars, and you can prefer whatever you want. You can include stars, you can not include stars. Sometimes stars are kind of disturbing. Another way to create the same regressions is to include the formulas right inside the formula that you define. Look, for example, instead of creating separately a variable log income, as we did here, I can write inside my formula this np.log_f_inc, and it will do the same. It will create logarithm of average income, and it will include this as a regressor to my formula. So in this case, what is nice that you don't need to create these additional variables. All the variables you have, you can use them. Well, except for this binary variable. Binary variable still must be created. All the other variables are not necessary to create. So for example, log variables can be included right away, and also squared. So with squared, it is slightly different approach. Look how we must use a syntax when we want to include squared or cubic terms of some variable. It's not simply str squared. It must be written like I and n in parentheses str squared or str cubed. The interaction term is written in the same fashion, no difference. This is just another version how you can write those additional variables in your regression models. You can choose whatever you want. You can choose this one, which, as I said, which does not require creating new variables. You can choose this one, which sometimes looks more elegant because you don't have this frightening things in your formulas, but it requires the creation of new variables. Whatever you prefer, you see I'm usually showing you different approaches to solve the same task. You can choose whatever you want, and I don't mind. You can find out even like some third or fourth way to solving these problems. This is uh, fine, and yeah, we can combine this, what we know, with another way to estimate regressions that we used, like this sm.ols, when we created the constant first and then we used smols. It's also possible. Just
What
be
does I mean on the second table?
it's like an indicator, like 1 multiplied by this. This is just a way how this function works. And as I can understand, so this is my suggestion, this form of syntax came from another programming language, R, which is used specifically for statistics and econometrics and data analysis. And the way how you specify these nonlinear functions in R is exactly like this. So I believe that it was replicated in Python just for convenience, to give people who are working both languages uh, the same format of representation.
Why don't we work in R?
I was choosing between these two. Yes, this is a nice question. When I started teaching this course, I was choosing between R and Python, and my decision was that R is it's more concentrated on econometrics and statistics and data analysis. But Python is more versatile, so probably in your future you will not need data analysis, but in Python you can do some other things like creating some applications, writing internet sites and so on. So maybe for you it will be better skill to be familiar with Python and not be familiar with R. But if you're okay with Python, you can easily transfer to R, and well, just sometimes it's confusing because functions are different and you're constantly trying to figure out, well, this function works in Python, this function works with R, but well, internet search helps.
It
Yes,
just
so
happened that we used R during our IT courses.
I didn't know
Because
about
yeah,
this. Yeah, if I would know, I probably would use R. But now you're more developed and skillful because you have two languages instead of one. Well, okay. So here how we can create and replicate these results. Please, as I said, use whatever you want. Try using these methods on, for example, this self-study, just to try that everything works before the last home assignment. Now, what I wanted to do. I wanted to do three things. We have half an hour, which is totally fine to finalize. First, last exercise session, I failed to give you the second way of testing joint hypothesis. So let's do this because the mistake was very stupid and very simple. So therefore, we will do this. So second, I will show you how to interpret these results, what all these numbers mean, and how we should choose the, let's say, the most appropriate model. And the third is just to understand, well, what finally do we have? Do we have a significant result of class size on the test scores or not? So how should we treat all these results? So first of all, you see that in the table here, down here, we have a lot of different joint hypotheses diagnostics. So one joint hypothesis is that str variables and interactions equal 0. So which means that in the case of, for example, regression 3, the hypothesis is that this coefficient is 0, this coefficient is 0. Oh, no, sorry. This coefficient is 0 and this coefficient is 0, the interaction term. In the case of column 4, we also have a joint hypothesis that this coefficient and this coefficient are 0. In the case of column 5, we have hypothesis that this coefficient are 0, 3 coefficients, and so on. So here we have 1 to 3 coefficients and also 1 to 3 interactions. So in total 6 restrictions. So let's remember.
Why str? Why fifth str is 0?
Which str?
Fifth column. You said that this is
Yeah, I mean, we are testing this hypothesis. It's not 0, but we are trying to test this hypothesis that all coefficients where str is present are 0. And in this case, we have 3 variables where str is present, so coefficients on them are 0. Here we test the joint hypothesis that the function is linear. The relationship between test score and str is linear. So let's try to test several things. So first of all, let's test the joint hypothesis on regression 3 that both coefficients on str and high L times str are 0. Why can we be interested in this hypothesis? Let's see. In the third regression, this coefficient single test says that this coefficient is not significant. A single test here also says that this coefficient is not significant. Well, and it may lead us to think that in this regression, str doesn't matter at all. The same happens in the fourth regression. Look, in the fourth regression, when we control for the average income and the percentage of those who are eligible for the lunch, we see that single coefficients, this one and this one, are not significant as well. It may wrongly lead us to think that str does not matter at all. And that's where we need this joint hypothesis. Because remember that even if you are not able to reject null hypothesis for this individually and for this, it does not matter that you are able to reject the null hypothesis that both coefficients together are not significant. So this is an important thing. So that's why we want to test this hypothesis. How would we do? We can formulate this hypothesis as previously we did. It was here in the end of our last exercise session. Here we formulate hypothesis and then we apply the method f-test for our regression results. So hypothesis is, in parentheses, we write this str equals 0. So let me rerun one thing. Yeah, be careful, guys, because we either use this or this. And in these cases, you must be very careful with the syntax, because if you are using these results, the syntax will be different to this. So just please try to remember which one you ran the last. So let's first let's run the first cell, the first version, in order to do this. So this is the first hypothesis, and the second hypothesis is that high L colon str equals 0. So this is very simple. Wait a minute, equals 0 here inside the parentheses, of course. The way is very simple, right? You simply look at the table, you simply look how this regressor is included, so how it's written there, and you provide the same here. So now we are trying to do this on results 3 object, this one, results 3. So we print results 3, f test, and inside of this we provide a hypothesis. Here is an f test. So let's compare the result of this f test with what we have here. 564, the f statistic, and p-value 0.4%. So basically we reject the null hypothesis, right? We reject the null that both coefficients are 0. And this is somehow confusing, right? Because this single coefficient is 0, or at least we cannot reject this hypothesis. This single coefficient is also 0, but together they are not 0. So one of them is non-zero. Well, basically we would prefer that the first one is not 0, right? So the interaction term does not matter, but this of course matters. So this is one way to test the hypothesis, and you are familiar with this, and you have the same in home assignment number 4. So the other way that I wanted to demonstrate you here with these zeros and ones. Well, let's do the same. Let's try to replicate this results f test. And now look, I was trying to put this in parentheses, but the correct way is to put this in square brackets. So last week I just demonstrated you what happens if you are not attentive enough to the symbols that you are using. If instead of parentheses you are using, or instead of square brackets you're using parentheses, well, you will obviously fail. So one set of parentheses and then the other set of parentheses inside that contains zeros and ones, and as I was explaining you last time, one must be placed on the coefficient that you want to test, that you want to include in the joint hypothesis. So which means the first 0 is constant, we don't test this coefficient. The second place is a coefficient on STR, we want to include this in joint hypothesis. And then how many regressors do we have? 1, 2, 3, 4. So 4 regressors in result 3. Let me check it here. 1, 2, 3, 4. Yes. So the rest 2 are zeros. So this is the first part of joint hypothesis, this part. So basically this human readable STR equals 0 and this in square brackets 0, 1, 0, 0 are equivalent. So now in the second, so you put comma, and in the second set of square brackets you provide the same sequence of zeros and ones, but now you put 1 on the place of this regressor of the interaction term, and this interaction term is on the 4th place. Intercept, str, high L, and then now this. So we write the following sequence: 0, 0, 0, 1. When we run this, we must have exactly the same result for the f test. So I believe that the first one is somehow preferable, it's human readable, looks nice. The second one, well, as I remember from the second part of econometrics, in some cases we would need this second one because the first one will not be working, or at least it will be not that suitable for some tasks. So that's why I'm always showing you several ways to do the same thing, because sometimes one is more appropriate, sometimes the other is more appropriate. So, and in this case, we see that str matters. Str matters even in this regression number 3. And also let me show you how to test one joint hypothesis for linearity. So, for example, we can test the joint hypothesis on regression 5 here, that str squared and str cubed, so I'll write it like this, or like this, str2 and str3, that coefficients on str2 are 0. So the same thing, we are trying to test the hypothesis that the relationship is linear with this f-test. So what should we do? We formulate hypothesis in the first parenthesis. We write str2 equals 0. In the second, we write str3 0. And now we apply f-test to results 5, not 3. Be careful because we are working with this. So results 5, f-test, hypothesis. And here we are with the result. So 617, and this is 617 here, this number. So you can try yourself doing all the rest. I mean, that's not the important thing for us here. There are also some tests for the interaction terms separately. I'm not going to do all these things. So my goal now is to show you how you can test the joint hypothesis, and how in the case of nonlinear models these joint hypotheses work. So basically in this case what we can conclude, we can reject the null hypothesis, we can reject the null of that's coefficients on str2 and str3 are 0. And what does this mean practically? Practically, it means that the relationship between str and test score is what? So what is the practical meaning of this rejection of the null hypothesis?
Just a second, something doesn't work. Ah, my code doesn't work. This, like this.
Maybe somebody else can help answering this.
So
what would this mean if we reject the null hypothesis for this joint hypothesis? Vladimir is silent today. Vladimir is not with us.
Vladimir is not here today. He is taking his dog to the vet station.
Okay.
If we reject joint hypothesis that str2 and str3 are 0, then it means that it has nonlinear regression.
That's true. So practically this means the relationship between test score and str, conditional, of course, conditional on all other, or controlling for other for economic characteristics. is nonlinear. Yes. So what does this addition means? It means that, well, we have these control variables included in the model, number 5, so the economic background variables, and also the percentage of English learners here, and controlling for these characteristics, the effect of class size on the test score is nonlinear, which means that if we have two similar districts by percentage of English learners, by percentage of those who are eligible for subsidized lunch, by income, so two exactly similar districts, then if one district has smaller classes than the other district, the relationship is going to be nonlinear. It will depend on the level of this STR. If the class size is large enough, so probably there is going to be, well, we need to see stronger or weaker effect. And if the class size is very small, so maybe the result, the effect is going to be, again, either stronger or weaker, but logically we can expect that if the large class is reduced, the effect must be stronger. If the small class is reduced, the effect must be smaller, let's say more moderate. So this is about joint.
Controlling for economic characteristics means holding everything else constant.
Exactly. As I said, if two districts are exactly the same by percentage of English learners, percentage of those who are eligible for subsidized lunch, and have the same district income. So this means holding everything else constant. All the characteristics are similar, but we are now changing in these two districts STR, and if STR in one district, initial STR is larger, then the effect is going to be stronger compared to another district with the same characteristics but lower STR. In this case, the effect is going to be weaker, probably. We need to calculate this. Yes, so this is about testing joint hypothesis. Now I wanted to show you the meaning of all these things. So first and second are okay. We've been doing this, and there is nothing very interesting. So let's have a look on the regressions 3 and 4. So, well, basically it doesn't matter which one. And let me just put everything in front of you, just to
May I
understand.
interrupt you?
Yep.
About the code, it still doesn't work. The error is expected an operator not 2 in the line str2 equals 0. What does it mean?
Well, check that you ran this first set of regressions first. You don't run this part, and then try to rerun this hypothesis.
Oh yeah, now it works.
Yes, I believe, because if you ran this part, well, let me demonstrate, okay? Let me demonstrate this case. If you run this part and this version of syntax, then in your hypothesis you need to provide exactly this version of syntax. So, like this.
Oh, I see. That's what you
And
said.
yes, and I also need to put these spaces here and here. Yeah, it will work with the spaces, because you see how it treats. It puts spaces here and here. So that's why the spaces must be there. That's what I said. So be careful with which set of regressions you ran. Yeah. Well, back to interpretations. So we have something like this. Test score equals, well, we don't have intercept here, but okay, it doesn't matter. Basically, it doesn't matter. So something which is intercept and control variables plus. What is the most important for us is this str variable. So minus 0.97 str minus 128 high L times str, and also plus here must be plus 564 high L. So this something, just this something includes all includes intercept and control variables. We don't care about them. We care only about these estimates. Now, let's try precisely to understand what happens with this. For the districts, with str, with high L, equals 0, the regression line is, or regression model, let's say, is. So we take our regression model. So this something is there, nothing changes. str is here. Now high L, if it's 0, this drops. If high L is 0 here, this also drops. So now our regression model is something like this, right? When str changes by, let's say, 2 units, the expected effect, the expected increase in test score is what? 0.97 multiplied by 2, which is almost 2. 0.97 multiplied by 2, 194 points. For the districts with high L equals 1, the regression model is. So let's go back here and let me borrow this line. So what happens? Something is here, 0.97 str is here, 564 multiplied by high L, which is 1. So 564 is here. So let me just move this to the left. It's here. And now high L is also here. It's 1. So 128 multiplied by 1 is 1. And we have the following. And now I can take 0.97 plus 128. So I guess I have 225. 225 str minus. Which means that when str changes by 2 units, the expected increase in the test score is going to be 4.5 points. That's what we have been talking about yesterday. For the districts with the percentage of English learners above 10%, the effect of the class size reduction is stronger, is assumed to be stronger, let's say. But in reality, we see that this interaction term is not significant, but the interaction term is not statistically significant. Therefore, there is no difference between districts with large and small percentage of English learners. If this interaction term were significant, then we indeed have two different regression lines with two different effects, and this effect is going to be stronger. What you must understand is the following. If you have a binary variable and you have an interaction between this binary variable and the regressor of interest, then in order to understand these numbers, you simply plug 0 in one case, 1 in the other case. You have two different models, and based on these two different models, you consider what is going to be a causal effect of changing your variable of interest on the dependent variable, as I did here. Any questions here about this?
Can you scroll up a bit to the regression? Yeah.
So once again, we don't care about control variables. You see that they even decided not to report them in the table, these coefficients. That's the purpose of control variables. So control variables, they somehow ascertain that the regression and the coefficients are not biased. That's all. This is the whole their purpose, but we are not interested in them, so we don't look at them. So that's why I'm just putting here this something, and that's it. Of course, if you want to do the prediction, for the prediction you need to know all these coefficients. But if you don't care about prediction, if you just care about the causal effect, no need. So let me briefly also comment on the regression number 6, because regression number 6 is very interesting here. We see that there are also the interaction terms between high L and STR. So let me do this fast. Regression number 6 is also something, and then we have this nonlinearity. So we have 8370 STR minus 438 STR squared plus 0.075 STR cubed. Look, when high L is 0, these, and these are also 0, because you see that I'm multiplying high L by STR. So that's why, again, for high L equals 0, we have these. This is not regression line anymore. This is the regression curve, because it's a cubic. And the effect, marginal effect of STR on test score is, what do we need to do? We need to take a partial derivative of a test score on STR, which is this test score partial STR, and there is going to be minus 8370 minus 876 STR plus 0075 times 3, 0.225 STR. So now if STR, for example, if STR equals, let's say 20, then this effect equals to minus 8370 minus 865 minus 8370 minus, right? So there's,
shouldn't this
why minus? Must be plus, right? Must be plus.
Yes, and also STR, shouldn't it be squared?
This one, you're right. Yes, it must be squared. You're right. So 8370 minus 876 times 20 plus 0225 times 20 squared. So this is expected, let's say, change, so linearized change in test score. Test score when we change STR by a small amount. Remember the meaning of derivative. So it's this, let's calculate this quickly. It's this multiplied by 400 minus 86 times 20. Yeah, must be minus plus 8370. Yeah, so it's minus 1.5. And when, for example, STR is smaller, let's take 18, then there is gonna be this, there is gonna be this, and we do the following. So 18 times 876 minus plus 8370 plus 0225 multiplied by 18 squared. So yeah, minus 108. So definitely for smaller classes, for the smaller classes, the effect is weaker. Because if STR is smaller, you see that this effect is smaller. So if we reduce the class size for the class of 20, the improvement in the test score is going to be 3 points. If we reduce the class size from 18 to 16, for example, the expected approximate, it's not an exact, it's approximate improvement in the test score is going to be 216. Again, don't take these numbers as the exact changes. Those are approximates because we are doing the derivatives, and derivatives are the linearized changes. And the last thing, for high L in this regression number 6, for high L equals 1, what do we have? Now we need to take this STR and also this interaction term, minus 1 to 3.3. So there is going to be something, and now I'm taking 8370 minus minus 1 to 3.3, and there is minus 39.6. Minus 39.6 STR. So on the squared term, there is 438 minus and plus 612. So there is 612 minus 438, which is 174 plus 174. And here we have 0.075 minus 0.101, this one. And this is minus 0.026. 0.026. So you see that we implemented in one function 2 different functions for 2 different groups of districts. For one group of districts with small number of immigrants, and for the district with the large number of immigrants, and we kind of packed all this in one model, which I think very nice. Now the marginal effect we can also calculate it. So it's minus 39.6 plus what's that, 348, right? 174 times 2, 348, and 0.26 times 3, 0.078 minus 0.078. And now you can also do the same. You can compute how much is going to be the approximate change in the test score given the class size of 20, and how much is it going to be for the class size of 18. So this is this plus 348 multiplied by 20 minus 30. Yeah, minus 1.2. So this is, let's say, moderate change, and for str18 is this in here, squared here, 18 squared multiplied by 0.0078 with minus plus 348 times 18 minus 39.6 minus 223. So what is interesting here, 232, that for the large classes, the effect is weaker. And this is interesting. You see that now we made something very amazing. That's really true. Now we are able to answer not that simple question how the class size affects test scores, but now we are able to answer how the class size affects test scores in different circumstances. Given two different groups of districts, one district with large amount of immigrants, of English learned students, and another with the small number of immigrants, we see that reduction in the class size in districts where there is a lot of immigrants has a better effect when the class size is initially smaller. So in large classes, this action will not have a large effect. Compared to the districts with a small fraction of immigrants, because in districts when there are students who are not English learners, the effect of a class size reduction is going to be stronger for large classes, not for the small classes. So, very complicated thing, which is not that simple. I mean, you are not simply claim that the class size reduction definitely increases the class the test scores. You are saying that this effect is going to be stronger if we are reducing class size in districts when there are a lot of or at least when the percentage of English learners is larger than 10 percent, and when the initial class size is already small. Otherwise, the effect is going to be weaker.
Also, shouldn't you include high L in the regression function? The last one.
It is
I mean,
included
in
here.
the Word file.
It does matter. It does matter because
okay.
we are talking about the effect of STR on test score. High L is going to be included in this something. Yeah, I agree. It's going to be something plus 816.1, but it doesn't matter. When we take the derivative, it just drops. Yeah, you're right. You're right. We can.
Oh, I see. Yes.
And one, the very last thing. So basically, we can say that this 6 regression is the most versatile and is able to explain and answer us a lot of questions about the causal effect of STR on test score. And well, this is as I said, this is the top of the whole course where we've been heading to. I also wanted to show you that after yesterday's lecture, I decided to include several additional slides to the lecture. So please don't ignore them. They will probably help you to do better on your final credit test and on your home assignment. I included these. So I briefly mentioned in the lecture about these effects when something changes, and here I put these calculations explicitly. So I was showing you those calculations in the Word file, so now I put them explicitly. For example, what happens to the test score if average income increases. So I put all these numbers here for you to see how these effects were calculated exactly. Also, I did the same for the log specifications. I put, so you see that we finished our discussion about log specifications here with these three models, but then I described them one by one explicitly. So for example, the first log specification is this. Here is the meaning of the coefficient. Here is the way how we can predict numbers with the help of this specification, and how we can calculate the effect of average income on test score. Then I take the second specification, then I take the third specification, so everything is described. So there are like 5 new slides. Please go through these slides, and yes, and I also included this discussion that I said in words, but I didn't put this on slides, about R squared and the fact that R squared is not appropriate to use when you compare two models. One is logarithms and other in levels, because those are not comparable. Regarding this, I guess everything was given and everything was explained, so no need. Yeah, so now I guess I gave you everything that I have in my mind about econometrics. So now your task is to take this, understand, and start using. Questions?
I have a question, not regarding this exercise session, but I just was wondering again about the last home assignment. First question was regression function, and how can we create this regression table and include not the numerical variable that was education, but transform it into the categorical and include in the regression function, and then print the table.
But I showed you today. Look.
Well, yes, I see this. So, and we have now data high L, and we can just simply put high L into the regression, into
So
the
for
model
example, look,
result.
if you want to regress average income on high L, and that's all. I mean, no interaction terms, nothing. So you simply do something like this. So test score on high L. So next, what we do, OLS formula, data equals data, and then, so this is gonna be okay. So let's call this results equals, and then it's gonna be fit conv type HC1, and then print results. What's wrong? Summary. Yeah, so that's it. So we defined this binary variable. We included this binary variable in regression, and that's it. Nothing is new.
Yes, how nothing see. It would be nice to know this before the home assignment.
Okay, so sometimes you need to solve the new problems for you. This is also a part of education.
Okay. So
if you want to include the interaction like str and high L and str, this is going to be like this. You see that we have basically reproduced the column number 3.
now I see.
Great. At least in the home assignment number 4, there is not going to be this binary variable. Don't worry. But you have some bonus also points in home assignment, so they're somehow substituted, right? So you lost something here, but you can gather some points from bonuses.
Which bonuses?
So I put in home assignments number 3 and 4 and 5, one bonus question for 5 points. It was explicitly
okay.
said that the home assignment is for 10 points, but there is a
I remember
bonus
now.
question for 5 points, right? So we can always somehow substitute the lost points from the binary variables, for example.
Yes, okay.
Anything else?
When will we have the review on the last home assignment?
You mean these number 3?
Uh, 3, yes.
Well, for me now at least it's more reasonable to kind of to just exchange messages. I'm still not I still don't see what was the problem with your